So what is voltage? It's one of the biggest concepts that we'll deal with this semester. It's energy per charge. And why is that? That's what we'll see here. So let's take a positive charge at the origin like we frequently do. It's producing an electric field. And let's also imagine that there's a test charge like we often do. This test charge is sitting at some initial position, and we're going to bring this test charge up to some final position and ask ourselves, how much work is that going to take? The work to push the test charge will equal the force times distance. And that's the work that you will do. And the force will be the force that you exert against the electric field. We can rewrite that as work is equal to force times, we'll just talk about the radial distance, r here. So if we have, let's say just a little test charge right here, the electric field is going to be producing a force on that test charge Q naught, and you will be exerting a force in the opposite direction. The problem is we can't just calculate the total work this way, because what's happening to the force? The force is changing. It's small when we're far away, so we have less force over here, and we have more force if we get closer in. But what if we write the force as the ratio between the work and the distance that we push at a given distance from the origin? Let's say we move just a tiny little bit. We will do a tiny little amount of work over a little tiny dr. So we can write this as dw over dr, and we can now use calculus to integrate over the distance and determine the total amount of work. Let's write our differential work times our force times our distance. The force, we know that the electric field is defined as the force divided by the test charge. And we know that our force that we exert is in the opposite direction, so we can substitute now for the force. It's going to be negative Q naught E times dr, and now we can find the total work. And our total work is going to be equal to the change in energy from our initial position to our final position. Taking the integral, moving out the negative sign and Q naught, we have the integral of EDR from initial position to a final position. But this here is somewhat inconvenient because we know that Q naught is small. It's basically 0, so that doesn't make sense because our total energy is not 0. What do? What if we divide by Q naught? And then we would have the energy divided by the charge that we're moving. We still have our negative sign. We're still going from the same position. And now we have some new quantity, but instead of talking about the energy per charge all the time, we're going to call it voltage. So we call this energy per charge. Voltage, we have the voltage at a final position minus the voltage at our initial position is equal to the negative integral of the electric field over the distance that we're pushing. And that's voltage.